Okay, so now reverberation in X-ray binaries.
Okay, so apologies for that. So I will talk more about reverberation and reflection, but in terms of doing this with X-ray binaries. And it turns out, due to the differences in the timing properties of AGN and X-ray binaries, if you make a huge stride with X-ray binaries, much bigger than you do with AGN, and I'll describe why. And so STROBE-X will actually will be revolutionary for X-ray binaries in terms of reverberation. We've already heard two talks about reverberation and reflection and also reverberation. I don't want to go in, talk through why we get reverberation again, but the difference that I do want to point out with X-ray binaries is that because the disks in X-ray binaries are hotter, they fall in the X-ray part of the spectrum, and so we also get to see reverberation from the accretion disk itself. So you not only have the ion line and the Compton hump, but you also pick out the accretion disk. So this is just a reflection spectrum of GX339-4 from New Star in red and blue, and from Swift in black, right? So this is covering basically the same energy range as we will with the XRD in the lab, right? And so you can see that we will be able to pick out the disk, the ion line, and the Compton hump with STROBE-X. The basic idea, as Abdu talked about, is we're trying to determine the time lag of each of these components, which is a function of energy. It also depends on the Fourier frequency that you look at, because these things are timescale dependent. Given we've already heard about AGN, let me just do some comparisons with AGN, just to give you maybe a bit more of a feel for things. All lags and frequencies will scale linearly with mass. So we're going to be talking about time lags that are a factor of 1,000,000 shorter than in AGN, and we'll be talking about similarly frequencies that are a factor of 1,000,000 higher than in AGN, right? So we should expect reverberation lags of the order of 10 to the minus 3 seconds on frequencies of something like 1 to 10 hertz in X-ray binaries for black holes, right? Just to give you a comparison with AGN. So there's a factor of 1,000,000 difference in terms of the size of the lag and the frequency, but there's not a factor of 1,000,000 difference in the flux, right? So typical X-ray binary, GX339-4 in the low hard state is something like 0.1 crab. This is the typical state people have been doing reverberation with in X-ray binary so far. Comparison with a typical AGN, talking about a couple of millicrab maybe. And so there's a factor of 50 difference in the flux, not a factor of 10 to the 6. This actually means that AGN and X-ray binaries are in a quite different regime in terms of the statistical properties, the time properties. So with AGN, you have many more counts for time scale of interest, right, through the cycle. So you get more counts per cycle, but you get far fewer cycles. So for instance, we're looking at a reverberation lag in an AGN. We're talking about something like a time scale of 10 to the minus 4 hertz, right? So in a typical 100 kilosecond observation, you will get, say, 10 cycles of that, right? Now, in the X-ray binary, and because there's only a factor of 50 difference between the fluxes, you get many more counts in each. You have far fewer cycles, but many more counts per cycle, right? And the X-ray binary, however, we're, say, looking at things with timescales of maybe a hertz. So we get 100,000 cycles for the X-ray binary, but the number of counts we get per cycle is far fewer. And that actually makes a big difference in terms of the noise properties. It actually means that you make a far bigger gain by going to a larger effective area with X-ray binaries than you do with AGN. This is important for the improvements you'll make with STROBE-X. It's also important for considerations in how drastically you'll affect those improvements by de-scoping things. Okay, so I'll quickly I'll go through a review a bit of what's been seen so far in terms of reverberation in X-ray binaries. The first clay detection was made in GX339-4 in the low hard state by Phil Utley. And all these plots here show you time lag on the y-axis against energy. This is 0.5 to 10 keV. In black is the time lag. These insets show you the covariance spectrum plotted against the power law. And the covariance spectrum is just essentially telling you the amount of variability you have of a given frequency and a given energy. So you can see that the variability is dominated by the accretion disk here. And you see that on the lowest frequencies, the photons down here, the lower energy disk photons actually arrive first, right? The way that you read these lag energy plots is that the more negative lags are where the photons arrive first. And so here, see the photons from the disk arriving before we see the photons from the power. You see, as you go to higher frequencies, when you get to 2 to 8 hertz, things flip. And you actually see now the disk component is lagged with respect to the power law. And this is the signature of reverberation. So you actually we see different physical processes happening on longer time scales, lower frequencies. You see the disk bleeding. The basic picture here is that we think that you get mass accretion rate, fluctuations in the accretion disk propagating from the outer parts of the disk inwards on the long viscous type timescales. And on the higher frequencies, the light travel timescales, you then see the reverberation taking place. So it's when you go to the high frequencies, you start to pick out reverberation. This is thought to be the reverberation from the thermal accretion disk, right? You see there's maybe something, there's some structure here at the ion line, but it's certainly not enough to be able to claim you've detected ion K alpha reverberation lags with XMM. So here's just a schematic basically showing what saying in pictorial what I was trying to say in words then, that on low frequencies the disk leads. This is not reverberation. On high frequencies you see this reverberation signature here. Right? And that's what we will try and pick out with STROBE-X 2. A lot of this work is recent work has been done by Barbara DeMarco. She's been successfully going through the XMM archive, trying to find these lags, and she's made the most progress with looking at GX339-4, and has found the lags in many different objects, so many different observations now. Here is the typical hardness intensity diagram. Here's this turtle head diagram or Q diagram, whatever you want to call it, that we saw from Havrier earlier. And these observations where the lags have been measured are all in these sort of hard states over here at lowish luminosities. People expect, as Havrier described, that as you go to low luminosities, that the accretion disk should truncate. If the accretion disk truncates, then your reverberation lag should be longer because you obviously don't have a disk. In a disk, for it to reverberate off, the path length is going to be longer to the outer part of the disk. You should measure a longer lag if the disk truncates. Barbara seems to show some evidence that as you go from 2% of the exiting luminosity down to 1,000 of the exiting luminosity, there seems to be a transition in the lags, and you measure longer lags at lower luminosities, potentially suggesting that the accretion disk is truncated. As Javier pointed out, this is controversial in terms of it doesn't necessarily agree with the time average spectral fitting results. This is the simplest interpretation of the lag, is that the disk is truncated. There may be some more complications there, but certainly there's hints that this sort of thing can be just about seen with XMM. With STROBE-X, you would hope to be able to look at the lags all the way around here. You may be able to resolve it on such short time scales, you actually may be able to see the lags change on the time of the jet ejection event, right? So you might, if the jet is somehow connected to the accretion disk, right, and the jet is irradiating the disk, if the jet propagates upwards, you should see a change in the lag properties. And you may be able to do these things on the time scales that you to be able to see that sort of thing with STROBE-X. Of course, we don't just have black holes in X-ray binaries. You can also have neutron stars, and the highest frequency variability you see in neutron stars is kilohertz QPOs, and the frequencies are around about the same type of sort of frequency you would expect for orbital motion at the inner part of the accretion disk. So these are possible probes from gravity, and I'm sure we'll hear more about QPOs, and we will hear more about QPOs in the next talk. But people have also been able to measure time lags in these kilohertz QPOs. So what you do is you pick out either the lower or the upper kilohertz QPO, and you measure the time lag as a function of energy. We're now going a factor of 10 smaller in mass again from black holes, so the lags are getting even shorter. This is lags from RXTE data for the lower kilohertz QPO in a neutron star 4U1608. We're now measuring lags that are about 100 microseconds between the soft photon arriving 100 microseconds later than the 20 keV photon will. And this was, people tried this in the late 90s. There's been a resurgence in doing this over the last couple of years as more interest has become in measuring time lags again. This is one example from Didier Barret. There are a few other examples, and my student John Troyer actually almost completed trawling through all of the RxD archive and looking at all the kilohertz QPOs and the lags there. And we find that the lower kilohertz QPOs all systematically show this same thing, where the soft photons arrive later than the high energy photons. So is this consistent with reverberation? It appears not to be when you try and fit reverberation models to these. You find you can match the low energy part correctly, but with reverberation you would expect the Compton hump to take over above 10 keV, and that's not what you see in these kilohertz QPOs. So there must be some other physical processes leading to the lags in the low kilohertz QPOs. But where reverberation may be present is actually the upper kilohertz QPOs. And this is where we actually, with RxD, you really struggle to do stuff right now. This is 4U1728. This is data from work done by Philip K.A., Didier Barret's former student. Again, this is time lag against energy. This is the lower kilohertz QPO. Here is the upper kilohertz QPO. This is the best object for upper kilohertz QPOs. And this is the best signal you can get from any of all of the entire RxD archive. Right? There are very few objects you can do this with. You see that it's quite different lag properties between the two. These 2 kilohertz QPOs seem to be have different physical processes going on in them.
Are those observed simultaneously?
These are, yeah. Well, no, this is the entire archive averaged over frequencies. That's the only way you can pick out the signal.
But are they both on at the same time for the most part?
No, depends. Here you see the increase in lag as a function of energy. You even see at the very highest frequencies at above 1,000 hertz, above around iron, right? So this may be signatures of iron K-alpha reverberation in the upper kilohertz QPO, right? Again, we're really limited by signal to noise with RxTE. With STROBE-X, this should be trivial. Okay, so where are the gains going to come with STROBE-X? And I've already showed the equation actually that defines how the uncertainty in the lag measurement depends on the powers in the bands that you care about. And it turns out because these AGN and X-ray binaries are in these different regimes where with AGN you get the high count per cycle, low number of cycles, and X-ray binaries you get the low count per cycle but the high number of cycles. They have quite different properties and how the lag measure uncertainty scales with count rate. So Phil Utley in our review of reverberation, X-ray reverberation, did some simulations and compared with the equations and showed for AGN with a high rate of few cycles, the improvement in the uncertainty at the lag measurement goes like the square root of the count p. as you are familiar with just increasing exposure time. With X-ray binaries, however, different noise term dominates, and you actually find that the uncertainty improves linearly with count rates, right? So you increase the effective area by a factor of 10, you get a factor of 10 improvement in the uncertainty in the lag measurement with an X-ray binary, right? So you get much bigger gains for doing X-ray binaries with STROBE-X than you do with AGN, right? So the 2 orders of magnitude improvement in effective area over XMM really leads to a 2 orders of magnitude improvement in the lag measurement with STROBE-X compared to that. Another important point is that a 10 times larger effective area or brightness source is equivalent to 100 times longer exposure time. The scaling with exposure time is still the same, right? So that's also an important point to remember. So we saw these sensitivity curves, similar sensitivity curves for Abdu. Here's one that was in the proposal. This I think Philip calculated, right? And you can again, it just gives you the idea of how much better you do with STROBE-X as you do compared to XMM, and compared to Athena also, right? You do better everywhere at all energies. So you're going to do better in the disk reverberation. You're going to do better with the iron K alpha line, and you're going to, and it's the only place you're going to get the constant hump reverberation. Warning about D-scope. Because things scale linearly, a factor of 2 in area means a factor of 2 worse than lag uncertainty for X-ray binaries. Right? So this is important to bear in mind. It has a big impact. Resolution, energy resolution, is not such a bigger worry in terms of these. We've currently already been data up to energy bins that are bigger than the resolution of direct resolution, and we still may want to be doing that here, right? You're limited by the amount of counts you can get in an energy band. So you may be bidding to 0.5 KUE anyway. Right? So I started doing the simulations for this. I have I can do this for AGN very easily. For the X-ray binaries, it's a little more complicated. I have something that came out of my simulations yesterday. I'm not quite convinced it's right, so I didn't want to show it. But I show you what we expect. So I'm not showing errors here. This is the model, right? So I show you I can produce the lags. They're at the right size scale for what we already see in black hole binaries. No one has yet tried to model the lags in the black hole binaries that you saw, that I showed from Philip, these GX33994. So here I use those general relativistic rate tracing simulations to give you a transfer function, and say if I have a 10 solar mass black hole, I look between 1 and 10 hertz, what would the reverberation signature be like that I would expect? And here you see the accretion disk, the ion line, and the Compton hump. What's not included in here yet is that there's also other lags that you see in the data, and that's these log linear lags that increase. I can add those in relatively easily.
Is this a lamppost corona?
This is a lamppost corona.
Have you tried anything else to see if it's different?
No.
Is that easy to do in the context of the way the
No.
model is set up?
So when you go to extended models, you have to start worrying about timescales for propagating things from certain regions, and it's pain in the butt, basically. So I think it's most likely to stick with lamppost simulations, at least to start with, right?
Yeah, I think pre-mission launch, that's good.
Yeah. And so I'm going to be I will work on trying to get out exactly what uncertainties we'll get in the lags for XRC and LLM. What I will say is that you could just do the scaling. It scales linearly, right? So the figure that I showed earlier from Phil Utley All right, this is 175 kiloseconds of data with XML, right? So we will do a factor of 100 better in the same exposure time, okay? With XRC in that, right? You can also say, what's the time scale? I will be able to recover a thing that looks the same as this. Well, we get a factor of 100 better because the count rate. If we want to scale down the exposure time, that goes like square root. So if we want to do a factor of 100 better, a factor of 100 worse to be the same as this, it would be an exposure time that's 10,000 times less. So this should be 17.5 seconds of data with XRC on that, right? So you can see, you can start to really probe short time scales and look at how dynamic the corona may be as things change. If you see a flare over a short time scale, you can see if it changes the lights. Okay. So I will stop there. So the summary is basically that STROBE-X will be revolutionary for X-ray binaries because of this linear scaling with count rate. And the combination of XRC and LAD is super powerful. Getting the disk, the ion line, and the continental. Don't get that with Athena. I'll stop there. Thank you.